Not only, let's see what.
Thank you, Richard. So it's a great pleasure to be here, being invited by a very old friend of mine. I know class since maybe 30 years, and younger friends, Walter and Simon, and you guys in the audience. So this is work that I've been doing with Francesca, Simon, Francesco, and Jens. But this talk is mainly an introduction to Francesca's talk. So
Very clever.
she ended exactly at the same. Right. So all the easy question to me, all the hard question to Francesca. On the other hand, I mean, this work bears also on works done by also some of the people in the audience. So if anybody in the audience feels I'm not doing justice to her work, please tell me so that we write here a list of people that should be mentioned that I failed to mention. So the abstract is the following. So Pimsner algebras, I'll try to tell you what these are, as a total space of principal bundles. And this is out of a Fock space construction, so the tautological line bundle is a central object. Giesing-like sequences in K-theory, and examples will be quantum length spaces, at least subclasses of quantum length spaces, out of line bundles over weighted projective spaces. I won't be able to say anything about connections, but one of the things that we have been doing is that to put connections. So on line bundles, monopoles, higher rank, so not line bundles. This is one instance where there are no line bundles. So instant on connections. And I'll try to also give you some hint to T-duality for these non-commutative bundles. And I'll tell you right away what I mean by T-dual. T stays for target space. And it comes from string theory, but of course, this is a name only now here. So the usual U1 bundles, so the Giesing sequence really it's H flux. This is a tree form on the total space of a bundle. Grazie, Beatrice. Yes. Two line bundles, these are two forms on the base space. And this also gives an easy isomorphism between Dixmer duality class of E and line bundles over M. But let me only for the moment say about the bundles, how does it work. So this is a long exact sequence in cohomology, any sphere bundle. So in particular, if you have a U1 bundle, so you have here the K group, and then you integrate along the fiber. You go down to K minus 1, and then you cut product with the Euler class of the bundle, K plus 1, pull back, and you start again. So in particular, if you start with a tree form, so H, a tree form, then you integrate along the fiber. This is a two form. So this is a two form. I mean, I will not distinguish between the representative and the class. So this is a two form, so this is the first shell class of a bundle E prime. So you have another bundle. And so here you have E and E prime. And now you write the sequence for the E prime bundle. And you have the same phenomena now. And in particular now you take the cap product with the C1 of E prime, and then F prime is equal to 0. So this means that now you can find an element in H prime, you can find an element H prime in H3 of E prime, so that integrating along the fiber you get a two form, and you want this two form to be the Chern class of the previous bundle. There is some ambiguity, the pullback of three forms on M up to E, but this can be taken care of. So now these two bundles, E with H and E prime with H prime, this will be T-dual. And there is a series of beautiful papers by these people where they put all this in the context of twisted K theory and many, many interesting things out of this construction. This is difficult to generalize to quantum spaces, so one rather go to K theory, where in fact this sequence becomes a very well-known object, a 6-term exact sequence. And here is how it works for projective spaces. For the moment, these are usual spaces, okay? So the projective CPN as a quotient of the 2n plus 1 dimensional sphere. Then you fix an integer r, and then you take the cyclic group, it acts on the sphere. You put these spaces in a sequence of principal band, and you have this Gisin sequence in topological K theory. So K1 of the length, down to K0 of the projective space, K0 of the projective space. Alpha here is the analog of the cap with the Euler class, and so now we are just taking the multiplication with 1 minus L of minus R. L to the minus 1 is the tautological line bundle over CPN, and you take a power. I mean, you take a power of this line bundle. And so this alpha here is this multiplication. And then you go up, going to K0 of the length again. The zeros here are because K1 of the projective space is 0. Otherwise, you just close this into a 6-term exact sequence. So one of the use of this is that you can compute the K theory of the length by knowing the K theory of the projective spaces. So in particular, K1 is the kernel of this map, and K0 is the co-kernel of that map. And typically, these are torsion groups. I will show you how this works when you have a Q, which is different from 1 when you deform this sequence. But this will be pretty much what happens classically. OK, so let me tell you a little bit, assuming that I think everybody in the audience knows about spectral triples. At least that's what we assume that, but maybe not everybody knows about principal bundles. I mean, on non-commutative spaces. So here is U1 principal bundles. So take this Hopf algebra, so the dual of U1, so generated by an element. There is a coproduct. There is a co-unit. There is an antibody co-unit. Now, if you start with an algebra which carries a co-action of H, take the co-invariant of this coaction. This is a subalgebra of A. And so this triple here, A, H, and B, is named the quantum principal U1 bundle when this map here, the canonical map, is an isomorphism. So A tensor A over B and mapped into A tensor H via the delta. When this is an ISO, you say that this is a quantum principal U1 bundle. In fact, there is, since you have U1, really everything can be done at the level of graded algebras. And so if you now have an algebra A which is graded over Z, and it's easy then to give an H-commodule algebra structure. You just declare that the element in AN transform by Z to the minus n, and the co-invariant are given by H0. And so you have this nice proposition that was also written by Andrei and Jan. Where is Andrei? Where is OK. So this was written in one of their papers. So when we wrote it, then we found out that this was established by Francesca and Jens in their paper. And then it was discovered that, in fact, this was already in the... So A, H, and A0 is the quantum principal U1 bundle if and only if there exists finite sequences of elements in A1 and elements in A to the minus 1 so that you can break the identity of A in this manner here, in these two possible ways. And this really means that A1 and A to the minus 1 are projective modules of finite type. So they are finitely generated and projective over A0, and you construct do natural maps. So from A1 to A0 to the n, and then from A0 to the n to A1, these two natural maps where you use this, this eta and this psi, and then psi1 is an identity, is the identity, and then this is an idempotent. This idempotent tells you that A1 is finitely generated and projective, and similarly for A to the minus 1. The above result, in fact, in a sense, was already known in the 80s. This really shows that AH and A0 is a quantum principal U1 bundle if and only if A is strongly Z-graded, which means the following. So in general, AM is only included in AN plus M, but if this you have the equality, this is strongly graded. Or equivalently, the right module A plus minus 1 are finitely generated and projective over A0 if and only if the algebra is strongly graded. Okay. In fact, more generally, you can you have this nice result, which part of it was in this paper, and then there was something that was fixed later on. So if you have any group and you grade your algebra with this group, so you write A as a sum of objects which are labeled by element in G. Again, you have this property that you multiply, this is only included. And now you take the group algebra, then A is G-graded if and only if there is a right H-comodule algebra. Sorry, if A is a right H-comodule algebra for the natural coaction, so AG goes into AG tensor G. The co-invariant now will be the component of the identity. And so this triple is a non-commutative principal H bundle for the canonical map, which is what is written here, what you expect, if and only if A is strongly graded, and which is exactly the meaning that there is an equality here. Okay, and so the proof is really the same. I mean, you just have to explicitly write an inverse of this map, k to the minus, can to the minus 1, which was already written in this paper of 81. Okay, here I want to present a more general scheme, which I found really beautiful, and also has a physics flavor. And this general scheme is this the construction of Pimsleur algebra, of which I will only consider particular cases, but this can be generalized toward what are called correspondences. But here I'm just taking a particular cases. So, the right module A1 and A to the minus 1 as before, these are line bundles over A0. The slogan, a line bundle is a self-Morita equivalence by module. That's the slogan of this talk. What I mean by this? So if E is a right Hilbert module over an algebra B, so this means a few things. In particular, it means that there is a B-valued Hermitian structure on E. Then one has the notion of adjoinable operators. If B is a complex number, E will just be an Hilbert space. So if B is any algebra, then this is something more complicated. It's not obvious that an operator is adjoinable. Take all the adjoinable operator, and then take what are called compact operators or maybe endomorphisms. And what are these objects here? So pretty much like a bracket construction of Dirac of a physicist. So you take two elements in E, this module, and then you construct this operator, which is really using, so this is the bracket in a sense, and the ket bra. is using the Hermitian structure on E to construct an operator. So I assume, self-Morita equivalence, I assume that there is an ISO between B, which acts on the right, with K of E, which acts on the left. So it's a general fact that KE is Morita equivalent to B via E. So I'm assuming now that, in fact, K of E is a copy of B. And so from this point of view, E is a B bimodule.
Is your B unital?
Yes.
So this E is finitely generated over B?
It is finally generated over B, at least in all the cases that I'm considering. Yeah, at least in all the cases. Right. Actually, while this object is a line bundle, it's also in a different way. I will show it later on, in the sense that the rank of this object is 1 when measured by a suitable class in the K homology. So also in this sense. So if I compare like before, so A0 is B, A to the minus 1. I prefer A to the minus 1 because it's nicer. Is E, and so one looks for the analog of OE, which is, one looks for the analog of A, which is this OE, with this Pimsner algebra. And the examples that I will show briefly is that B is the quantum weighted projective spaces. E will be powers of the tautological line bundle. There is a notion of tautological line bundles over this object. And then the resulting Pimsner algebra, this will be a quantum length space. How does it work? Like I said, it's really, it's a physics flavor. It's really a Fock space and then a creation annihilation operator. So one use 5 to construct the inner tensor product. So E tensor E, and then this is made a B Hilbert module. So there is a right action of B. There is a B valued Hermitian structure, which is written like that. I mean, you use 5 to bring this to act on the left on an element of E, and then you just use the Hermitian structure on E. And there is also the dual, which I will write like e to the minus 1. So elements will be written like that, again using the Hermitian structure. And so I take all of them here. I take all the possible powers. So all the possible positive and negative being really powers of e to the minus, e star, sorry, e to the minus 1 being e star. And then for each element in E, one has a bounded adjoignable operator, and it's really a creation operator. So for instance, on B, you just act in the usual manner. B acts on the right on E. Then you have xi1, xin, and then you just tensor with xi. Or if you have lambda xi1, lambda xi to the minus n, and you have to play a little bit with the map 5, or 5 to the minus 1, and then the compact operator associated to xi1, xi. And so what is the Pimsner algebra? And the Pimsner algebra of the pair 5E is the smallest subalgebra of LO of E, which contains all these operators. So which contains all these creation and then annihilation operator. And Pimsner proves that this is universal with for some conditions. So and this is a very nice construction, a very nice result. Then this is a little bit okay. So to the next level. So there is a natural inclusion. So B is in OE, and I would think of it as a generalized principal circle bundle. I mean, in the sense that roughly elements in E of n, they behave like eta goes to eta lambda to the minus n. Here I'm acting rather than coacting, but it's really absolutely equivalent. And to have a principal band, I will need to show that this graduation here is really a strong graduation, but there are when this happens, this is a principal bundle. Otherwise, it's some kind of a generalized principal bundle. But let me not dwell upon this point more here. I will rather give examples of this construction. But roughly, what I have in mind is that B into O of E is a principal bundle. Now, I told you at the beginning that one of the objects that I wanted to construct was this Giesen sequence. But here it's really everything is in this paper by Pimsner. Although we did it by hand in one cases, and then I'll show you these cases, and then I think Francesca will elaborate on this and expand this construction in her talk. Really, the sequence is already in Pimsner. I mean, so there are two natural classes that you can construct out of these algebras. First of all, you have an element in K, K0, BB, and this is really E, the class of E, E50. Then the map 1 minus E has exactly the same role as before of the Euler class on when E was really a line bundle over an ordinary space. So really, the role of the Euler class is this map here, so of the line bundle over the noncommutative space P. Then there is another class which is a connecting class. So K, K1, OEB, this is an odd element, so you take E infinity. This is the inclusion, 5 of tilde is the inclusion into the adjoinable operators. And then F is really related to the projection onto the positive part. So F is P minus 1, where P is this projection. These are explicitly written in Pimsner paper. So you have then that you have a map from K star B into K star B, or K up B in K up B with the class E, or you just go up by 1 in the indices using this delta. And then Pimsner constructed this, actually does it in KK, but I mean, let me just do it for K theory and K homology. So where are we? Okay, K1 of the total space down to K0 of the base space, K0 of the base space, and now there is this inclusion of B into OV, so you go up to K0 and then you go on. Okay? In the example that I gave you before, and in the example that I will treat later on, this K1 is 0. So again, this 0 and 0. So there is only this part here. And there is also the dual where you just invert the arrow, but there is the dual map in K homology. In fact, in KK theory, but this goes really well beyond the scope of this. Okay, so this will be the analog of the Giesen sequence. So let me just then give you some example of this construction here. And the examples are actually by now, I mean, you see, when I was a student in physics, the example that they would use was the harmonic oscillator. Everything was the harmonic oscillator. Okay? Now, the example that I use is projective spaces. I mean, we are fed up. But on the other hand, they are so nice as objects that Okay. So, sorry for this. The spheres and projective spaces. So like the harmonic oscillator, okay?
Or quantum flowers.
which is even worse. Yeah. Okay. Right. So the quantum spheres and the quantum projective spaces. Although I should say that now we and also other people, the most recent paper being by Brzezinski and Wojtek Szymanski, these examples of length spaces have been sophisticated to all possible weights, and so it's quite getting wild. So this is a very complicated harmonic oscillator, in fact. But anyhow, these are a nice example to start with. So the sphere, the coordinate algebra, this is generated by a number of elements, and there are some relations, plane relation, and then there is one of the generator is normal, and then you have some other things here, and then there is a sphere relation. So when Q is equal to 1, so this everything collapses here, and you have only this. So this is really the algebra, the coordinate algebra, over the ordinary space. So this work goes back to Waxman, Soberman, and Berk. Maybe one also should mention Voronovich, actually, that also Voronovich constructed some of these spheres. So the subalgebra of this algebra here, the quantum sphere, which is generated by these objects, Pij. So this is made of invariants for the action of U1. So if you just multiply each element here, Z0, Z1, Zn, by lambda, then this is the algebra of invariants. So again, I'm using here an action rather than a coaction because it's really easier and it's less, I mean, you need less writing. So this vibration here, this vibration, S2n plus 1 down to Cpn is a quantum U1 principal bundle, in the sense that the algebra inclusion here, so projective space into the sphere is a principal bundle in the sense there is a coaction or there is an action, and then the canonical map is an isomorphism. In fact, again, a previous paper by Hong and Szymanski showed that these are all graph algebras. By the way, this paper that I was mentioning shows that all these length spaces, projective spaces, weighted projective spaces are graph algebras. So if they are graph algebra, then you know what is the K theory and even the K homology. So in particular, for Cp and Q, this is the result. Okay, K0 and K0 up and down is n plus 1 copies of Z. Okay, so you may be satisfied with that if you play with these things, but you can do more. And what since one of the things that I would like to do, and we want to do, was to give a geometrical generators for these groups and geometrical representatives for these groups. So we, with Francesco, at least for this case, we construct explicit generators of the homology group of these spaces here, given explicitly as classes of Fredholm modules. So I won't tell you exactly what these are, but they are essentially, you see, a spectral triple will be an unbounded Fredholm module, let me say like that. So you have an algebra represented on some Hilbert space, you have a grading here, and you have an object which is rather the sign of the Dirac operator, okay? Loosely speaking, okay? So it's rather the sign. So instead of, if you have here a Dirac operator, this will be a spectral triple. But this is the analog of the sign. And you can construct n plus 1 of them explicitly. Okay? On the other hand, since on the other hand, since I'm also playing with these line bundles, we also gave generators of the K-theory group. And they were given explicitly as projections or line bundles in the sense now of modules of equivariant maps. So we construct the projections. I mean, again, or an idempotent, but in this case, it's really a projection. So you write P as a, you see, you remember what I was doing with L1 and L-1 before. I was writing psi 5. OK, so here I'm having a vector-valued function on the sphere. So elements here will be elements on the sphere. This will be of length 1. So if you just take psi n star, this is a projection. And so you can construct them explicitly. So elements of these projections are U1 invariant. So these are elements on the projective space. So these are elements in the K0 of the projective space. And we proved that really the first these mu's and this P up to minus n, they are generated of the K theory and the K homology by computing the pairings and showing that this is not 0. So we computed explicitly the pairing. All these traces were computed explicitly. So OK, so this is a basis. In fact, one can do more toward going toward this idea of line bundles and Pimsner algebra. Now, to any of these projections, there are objects here, so which are written like that. So you have your projection, and you act maybe on the right on copies of the functions, or maybe on the left with p n minus n. These now are, you can identify these as elements of the sphere which transform under U1 as this way here. So these are really equivariant maps of weight minus n. Okay, you may remember that if you have a principal bundle, G is the structure group, and then you fix a representation of G, then you construct the associate bundle. This is a bundle over E. Then the section of this bundle here, this is the same thing as maps from P into V, which transform similarly to that. So 5 of PG is really rho to the minus 1 of G, 5 of P. So equivariant maps of the weight which comes from the representation rho. Here U1.
Sorry, I mean G is to minus 1, not rho.
Oh, so, yeah, sure. Thanks.
Average. Rho of G to minus 1.
Right. All right. Okay. So the same as equivariant maps. Okay. I should. And so here I'm taking the representations of U1. These are labeled by an integer n, and so I'm just saying this. In fact, you have this nice property here that you can compose them. You can compose them over the function over the base, and then L m n plus m. By the way, if m happens to be minus n, then L minus n go to L0. So form of positive n form times minus n form are functions, which resonates with what our friends were doing, Latham and Shan. So, okay, so this you can, okay. So again, you can identify these things. So these objects, you see, again, I told you that I will tell another way to consider these as line bundles. So the modules are line bundles in the sense that the rank, as measured by the coupling with the first mu 0 is equal to 1. And on the other hand, the first share number, which will be the number that you get by coupling them with mu 1, this is, in fact, in this case, is n. So 1 minus n. So, so this will be why I'm calling them a line bundles. So this will be line bundles of degree minus n. And this also explains why I like L to the minus 1. Because L to the minus 1 is a line bundle, and then also the first number is 1. All the other numbers are 0. Mu 2 over L1, mu, they are all 0. So this is really a nicer object. So this is the analog of the tautological line bundle on this object here. And its Euler class is this nice object, 1 minus L to the minus n. In fact, you can use U as this object here as a multiplicative generator of the K theory. You can write that K0 of Cpnq is really Z over U with the condition that Un plus 1 is equal to 0. What do I mean here? You just take Un plus 1, measure it against all this mu, you get 0. So this object is 0. So it's, I mean, it may show up, it may be dressed as a beggar, but it's 0.
But
So
it's only additive isomorph. K0.
no, it's a no, it's.
What's the multiplication of K0?
I'm just using. So I'm just taking all the powers of U. You zeta 0 U, zeta U plus zeta U1, zeta U square, and so on.
But what was the product in K0 of CPNQ? There's no product. There's no product.
It doesn't say that.
This is,
This is module isomorph.
no, but I can multiply.
Additive isomorph.
Oh, I can multiply. I use this thing here. I mean, I can.
No, it's in the Kimsa.
What do you mean?
So these are five modules.
Am I getting something wrong?
So K0 consists of one-sided module.
Huh?
It is actually, in this case, a ring.
In this case, it's a ring. Yes.
It is a ring.
Yes. So what? Why it's wrong?
From KK.
In this case. No, Jens?
I will keep my mouth shut.
Which is bad for me? Or no?
Which is bad for whom? No, I mean, there's no product on K0. Now
Yeah, there is no product. Okay, yes.
No, it's not a ring. I mean, of course, you can define a ring structure, but yeah. It's just doesn't come from it.
Okay, it does not come from anything. That's good, but I can define it like that. Okay, can I go on? Huh? You need a bimodal, yes. Yeah. Yeah, I have it here. Yeah, I'm not saying this is true in general. I'm not saying this is true in general. I have a bimodal structure here, and then I'm using it. Is that okay?
That's definitely okay.
Jens is okay? If I have Jens' approval, I'm happy. So, no, I mean, in general, I don't. I mean, this is that. I mean, if this is a. I mean, I cannot do it in general because if I take a tensor product of a rank n object with a rank n, okay.
Since you're using as a definition of line bundle the fact that it's an equivalence bimodal, you can always tensor these.
In this case, I can do it. So. Oh, okay. Where is the chair? Chair. Right.
Yep.
It doesn't mean it if it's too. No, that is a product. You don't know what it is.
But the thing here is that
In this case, it
the
happens.
K theory of this space admits a representation which is in multiplicative notation.
Yeah.
So that's the
That's it.
thing.
Yeah.
It's
When you start a ring, it's a mod.
It's a module, yeah.
It's a mod.
It's a module, yes. No, no, keep on so that I can get some rest. I still have 20 minutes. So. No, but I can stop.
Francesca.
No, okay, so many of these structures are particular to this case, okay? So I'm not saying anything in general. I don't want to say anything in general, okay? So you see why I'm using the fact here. So what is this object? This object is really, these are powers of L to the minus 1. So in the sense that I was doing before. So I'm using heavily the bimodal structure. I'm using this fact here. L1 times or L1 is L2, okay? So I'm using heavily these things here. So in fact, there is only one object, L or maybe U, and I take power of L or maybe power of U, and then I get all the rest, okay? I don't want to say anything more complicated than that. So in particular, you see, if R is equal to 1, this is a way to write the function over the sphere as a direct sum of this object Ln. Here I'm taking R, which is any number greater or equal than 2. I'm just doing the same thing. I'm just taking the same thing. Okay, R equal 1, just breaking SU2Q into components which are labeled by an integer. So I'm just doing the same thing. If you do this, then you discover that this is an algebra. So I can multiply and do this. This is an algebra. And this is made of all elements which are invariant for the action of the cyclic group here. So on each component, I'm acting in the same manner. I have only one index. So more general things you can invent different indices here. Okay. So for the moment, I have only one index. So the dual object is the quantum length space. So maybe even dimension here you can object. I don't know. I mean, of index 2n plus 1 and R. There are algebra inclusions. I mean, and then there are principal bundle structure. So this algebra inclusion is a quantum principal bundle with structure group U1. Okay, again you have two quotients. Now, one of the things that we did really by hand was to pull back line bundles from CPN to the total space. So these arrows do not exist, of course. No? So you have this algebra. This algebra is in this other algebra. So you have this line bundle here. Then I want the line bundle over this space. Well, but this is not very difficult. So I just take the tensor product over CPN with the algebra of the total space. So I get this L tilde of this J star. And this gives induces a map in the corresponding groups. Now, one of the things that one immediately realized that, okay, all of these L of n were non-trivial, but meaning they were not free. But of course, this is not the case any longer when you just go up. And so in particular, if you take L to the minus R, and then you take its pullback, this is tautologically free. So L minus R tilde is really L0. So this is really, all of these, in fact, all of these pullbacks, they define torsion classes. In fact, okay, so there is this map. Then there is this other, so there is this map of pulling up bundles. Then also I want to use the L to the minus 1, or in fact L to the minus 1 to the R, and construct the corresponding Euler class of this line bundle. So this will give me a map from K0 of CPN to K0 of CPN. And so you can assemble this into this sequence. Now this was done. This was done before we discovered the Pimsner. Okay, so this was done in a paper with Simon and Francesca, and so we showed that this sequence, so K1 of the lens, K0 of the projective space, K0 of the projective, and so on. This is exact, and this map here, they are index maps. I think we used a paper which was Richard, and then Nesheyev, and Rennie, and Carey. Okay, and so, and also I'm mentioning here because I think Francesca will kind of evolve from here, right? Okay. So in particular, I told you already that one of the things that one can do is that one can compute the K theory of this lens space. So K1 is the kernel, K0 is the co-kernel, but also one can give explicit geometric generators of this group, in fact, in particular of this group here, which will be then pullback of line bundles from the CPN. And all of these generators will be suitable combinations or powers of, again, of this class, of the Euler class of the L to the minus 1. Just to give you an idea of this the structure, of course, the matrix alpha is rank n. You can show it. This is easy to see. So K1 is always Z. K1 of the lens space is always Z. On the other hand, the co-kernel will depend on the divisibility property of the integer R. So it may be a complicated group. So the structure will be something like that. Some of these alpha could be 1. For instance, if n is equal to 1, you get that K0 of L1R is Z plus ZR. And the generators, where is the generators? Is really the tautological line bundle. Or when R is equal to 2, you have that the K0 is Z plus Z to the 2n. This is for any n. When n is equal to 2, you have two cases, even and odd. Okay, so and then you can compute, and these are you can write the generators. Okay, let me just tell you a little bit about this T-dual line bundle. Okay, so let me go from at the very beginning. Okay. So what I did here, so there is a line bundle, I integrate along the fiber here an element in the third group, in the third cohomology group of E, and I integrate along this fiber an element in the third group of E prime, and these are F and F prime, and so one of them each of them determine the other bundle. So H will determine F prime, and H prime will determine F. Okay, and so in this, because you have these two sequences here, this sequence here for one bundle, and this sequence for the other bundle, and then what is crucial is this fact here. And since the sequence is exact, so F here is in the kernel of C1 of U or C1 of E prime, so there exists an H prime, so that F prime is the integral along the fiber of H prime. Okay, so it's using the fact modulo the arbitrariness. Let's forget about that. So I'm using the fact that the sequence is exact. So anything that is in the kernel here comes from something which is up here. Now, a similar phenomenon I can show for these Pimsner algebras. Okay. Yeah. Okay. So let me do it for CPN 1, so the line bundle. So this is the sequence. So K1 of the length space, down into K0 of the projective space, 1 minus L of minus R, K0 of the projective space, and then up again. Okay? Now, if you work out what is the kernel of this map here, the kernel of this map is generated by U, 1 minus L to the minus 1. So what you do, now take an element here, take an H in K1 of the length space, send it down via this map. This must be in the kernel, so this must, I mean, the easiest way to map is that you send it to H times U. But what you find out is that H, 1 minus L to the minus 1, this is the same as 1 minus L to the minus H. So you have now the dual bundle. So you start with the L to the minus R, and you found L to the minus H, R and H. Also, like it happens for the cohomology, one is in the kernel of the other. So this is in the kernel so this is in the kernel of this, and the other way around. So you can use here, one is in the kernel of the other. But so this means that if you can, sorry, not if you can, it means that if you write the dual sequence, the sequence for the other, now for H here, then you can, since the sequence is exact, there is an R in K1, so that R is mapped into 1 minus L to the minus R. So there is a similar phenomenon to there is a similar phenomenon to what was happening for the vector bundle. So that I have here now a length space, an element H in the K1 of this length space, and I have another length space and an element in the K1 of this length space, but these two numbers, R and H, are related, R, H, H, R. So I'll call this T dual. And this is an example of T-dual Pimsner algebras. So one can hope that one can generalize these examples this example in general, in more general situation. But before I do that some other times, maybe I want to also mention some more general work for which Jens was crucial. So, I mean, we wrote this paper, and then somebody was telling me, I mean, look, this looks really like pretty much like a Pimsner algebra construction. So I look, I Google Pimsner algebra. The first item is a master thesis by a guy named Jens Kaat, who happened to be in Trieste at that time. So I just knocked on his door and said, look, why don't you tell me what is a Pimsner algebra? He told me, and then I only learned a few things. But then we also construct these more general examples here. So now take the quantum weighted projective line. This was introduced by Brzezinski and Fairfax. So they also showed this nice fact that you can partially resolve singularities. So classically, K0 of this projective line, no matter what they are, the indices K and L, this is always Z2, okay? But now Thomas and Simon Fairfax showed that for this weighted projective line, really the K theory is ZL plus 1, L is one of the indices. In fact, they gave generators and relation, and you see explicitly that some of the singularity are not there any longer when Q is different from 1. So one can then construct more general quantum length spaces, which will now come with two indices, K and L, and this is the action of the corresponding cyclic group on the tree sphere. And so you map one by, now one, there is these two indices here, L and K. And in fact, you can also write that these length spaces a la Pimsner, these are a direct sum of elements which are labeled by, I guess this n is capital N. This n is the same here. And there is a central character again, which is L, I should be L to the minus 1. And so that you can write explicitly as a projective modulo of finite type. And in fact, then Jens and Francesca were able to compute explicitly the K theory and the K homology of these spaces. Okay, so in particular, if K and L are any co-primes, and then the K0 of this length space is the co-kernel again of 1 minus E, the E being, E being essentially L1. And this is the result where I is the inclusion of Z to ZL. K1 is now, instead of being only Z, now there is ZL, and also the dual theory, so the K theory and the K homology. And there is no dependence. One of the label really is ignored. Okay, one of the you see the two generators of Z0 and Z1 of the sphere. They have one is normal, a normal generator. So you see the effect of this fact in the fact that one of these label is not present. I think I'm pretty much at the end. This my grand motivation, my great, what I want to do when I grow up, gauge fields on noncommutative space, T-duality, Chern-Simons theories, and then I want to use more systematically this Giesing sequence, but I guess I should stop here and thank you for listening. I mean, there can be anything. K and R can be any number. Yeah. I take L of R, the length space we need the index R, any R which is greater or equal than 2. I take any element in K1 which I represent as a number because K1 is Z. I choose some unit, so it's again a number H. Anything, and then I construct the length space of index H. And then I'm able to show that the element in K1 which goes down is exactly the R before. So this H and R can be anything. Any greater or equal than 2. Okay. The connections? Oh, yeah. Oh, no, that's a very nice question. Actually, it's connection in the usual sense. I mean, there is our covariant derivatives. So there is a calculus. Oh, I can construct a calculus in this. I can construct explicit some calculus on. I can construct in I in the sense I Francesco and Ludwig, and okay, and maybe somebody else. There is an holomorphic calculus on all these C, P, and Q. I should say we in the sense of you see Tacito. You say we. And then, but no, but I want to say some other thing, another things. So this is something which goes from n of this L minus n into L minus n tensor omega 1, explicit. Explicit, okay? And then an Hodge star operator, explicit, so that this is true.
Yeah, but that's basically the same thing that you discussed, right?
No, no. What do you mean? Well, there is a lot. It's maybe Ludwig can tell you more, but there is a lot of representation theory. So, yeah, okay, it's an hard work. I mean, and you can construct on L so on line bundles. These will be monopoles, and you can construct also instantons kind of things. So, an object of the form L minus n plus Ln. Okay, an object like that. So this will be a rank 2. And so you have families, actually. You have families of connections which are parameterized in such a manner that somehow the boundary is the projective space you start with, the quantum projective space. So you have a family, a 5-parameter family of instanton connections, and you can realize that some of them really some of them are really a copy of the projective space you start with. This is actually, I should say, in CP on n equal 2. I mean, this is really, the calculus is in any dimension. C, P, Q, Qn, an holomorphic calculus is okay, it's there. But on CP, Q2, you have a monopoles and instantons. Actually, if you give me time, I can give you another talk on the connection. I need 1 hour. It's prepared even.
Friday afternoon.
Huh? It's prepared.
Friday afternoon.
Yeah. Sorry, but he always asks difficult questions. So.
For spaces more general than projective spaces.
Yes.
Even if you have this free action of U1.
Yes.
Then you obtain these weight spaces,
Yes.
which are bimodules, and you can apply these Pimsner constructions. It is well known that for more complicated algebras, multiplication of these direct sums inside the algebra is complicated.
Oh yeah.
So I wonder, what's the universal property of this Pimsner algebra?
You mean for in general? You mean?
Yes.
Okay. I guess I should really refer you to the book, to the paper by Pimsner. I can.
Does it relate to the multiplication of these sums inside the algebra and this free construction?
I think you should look at the.
The relation between, the product of psi and eta sine eta dual. I mean, this has to be a compact operator, and the other way around it has to be an element in the
Yeah.
algebra.
Yeah.
That's basically the universal.
Yeah.
formula.
Yeah.
So it's very clear. I mean, it's four lines.
Thank you. And not according to the schedule of you, I know maybe 5 minutes.
5 minutes.